はミケラ・クインタイン・コリンズさんです。Now, please welcome our next presenter, Ms. Mikerah Quintyne-Collins. Ms. Mikerah Quintyne-Collins, the floor is yours.
Hello. So today I'll be talking about Stoffel. Stoffel is a framework that we're building to enable multi-party computation. So if you think about blockchains today, everything is public by default. And although this gives us a lot of really cool applications, this also limits what you can build. The biggest thing is that you have no choice but to be public by default. And there's a lot of use cases, as we're seeing, that rely on private information. And as a result, this is hindering what we can build on top of blockchains. Why does this matter? Well, clearly, as you can see from the grid there, means that we can't really build all sorts of applications that we want. We are pretty close, depending on what tools you use. So as you see, this CowSwap, it doesn't really use advanced cryptography, but it does use some clever architectural decisions to be able to give decent amounts of privacy. Most centralized exchanges and DEXs that most people use have very high adoption, but no privacy at all. There's on-chain games that at one point were popular, but are no longer popular, and that have also have low privacy, low adoption. And then there's that other aspect where there's relatively high adoption, relatively low adoption, but high privacy, like turn-order cash, and a lot of shielded payment protocols. And so yeah, this affects what we ship, how we can adopt blockchains, and what you can add to apps. And despite solving scalability for most use cases on the previous slide, either through the use of new L1s or through L2s, we still don't have privacy. So even though you can have high throughput, bit 0, it's still 0 as it says on the slide. So really the next area of adoption is through being able to target the upper right quadrant there, as I've pointed to. It doesn't show it nicely, sorry. So as a result, adoption kind of stalls, and you're sort of forced to make trade-offs in your application design that are more centralized. For example, centralized exchanges sort of act as a de facto privacy tool for many people, and as a result, you get less people actually on-chain. They're still just using crypto through Coinbase, for example. Right now, we do have a lot of privacy tooling that can help developers. ZK is the most advanced, has the most mindshare, has the most tooling available, but you're limited in terms of what you can do with private data. Specifically, you can't really do computation over private data. By design of ZK, the data is meant to only be held by the user, and you should provide proofs about that data. So you can't really share it unless you sort of make assumptions about who is on the other receiving end of that data. Ts are seeing renewed interest and popularity recently, and there's been many gains in making them secure in practice and in the tooling as well. But the hardware guarantees are still making a few folks sort of worry about actually deploying them. FHE is also getting renewed interest and is being funded quite a bit. However, even for relatively simple operations like multiplication, it's still very slow. Requires hardware speedups, and as a result, many companies building sort of FHE hardware. MPCs provide the same functionality as FHE, but trades off this computational slowness for latency instead. But then your trade-off there is if you want relatively fast computation, then your nodes need to be relatively close geographically. So there's no tool that does everything at once. So as a developer, if you want to add privacy to your on-chain applications, and you want to be able to do expressive compute as well, then what are your options? So today we'll be talking about Stoffel. He's a honey badger. He's a real honey badger in South Africa, and so we named the company after him. There's a saying called the honey badgers are like the most resilient mammals. Beyond humans, they have very few natural predators, and so we named our MPC framework after Stoffel. So what is Stoffel? So it's a full stack that we've built specifically for MPC. I added TEs in here because we use them for integrity, but most of it is MPC. So we'll just be saying MPC for the rest of the talk. Basically, it abstracts away the underlying cryptography. The dev flows are very familiar, and it works regardless of the setting, Web 2, Web 3. I should note that our Web 3 stuff is still like work in progress heavily, but I'll be able to sort of go through examples on how it should work. So yeah, you don't really have to like buy a token to use it. You don't need to like fund a wallet to use it or anything like that. It's just like any other dev tool that you're familiar with. So quickly, what's MPC? It's a way to compute a function without a trusted third party. And typically use it when everybody that is computing with each other sort of distrusts each other in some way. But there's information that is beneficial to everybody. And so this gives us confidential compute while also distributing trust. A little bit of like a lower level detail here that I think is interesting is that in order to do MPC, the fundamental unit is called a share. And each of the Stoffels in this image would have like pieces of A, and that's what a share is. And so by the nature of MPC compute, this is sort of why we had to come up with a stack from scratch. And so these are like inherently distributed objects, pretty different from what you're used to as a developer. And there's some like nice or weird features about these shares. Addition is free, but multiplication incurs latency, and these can happen over fields or rings. So more concretely, what is the Stoffel stack? So we have a DSL called Stoffeling. It's still a work in progress, but right now it's very Pythonic. It looks very familiar. You don't really need to like completely rethink your syntax. We've simplified it quite a bit. So write the exact computation you want to distribute, to have running in an MPC network. We have secret and public types. The secret types represent the shares that I mentioned on the previous slide. And you have explicit control over when you want to reveal a share. So on the previous slide, this would have been reveal A, or if you want to keep brackets A. And the underlying cryptography is completely abstracted away, so you don't need to know what a share is to even use it. The main caveat, though, is that by the nature of MPC, there are some things that you can't do as you would with any like general purpose programming language, and control flow is one of them. You can't do conditionals is like the biggest one. Basically, if you do conditional, you would have to reveal the value. So you can't really do like if statements very easily. Next, we have the Stoffel compiler. So once you've written your program in Stoffeling, it compiles, and basically, not only does it provide bytecode, but it provides like the most like efficient way to execute the MPC program. And so this is what like the output looks like. We're making this cleaner so that it makes more sense for developers. Then this is the actual meter of everything. We have a Stoffel VM. It's a separate execution environment optimized for multi-party computation. So once you've compiled your Stoffeling program, you're left with the result of bytecode. And this bytecode is loaded by all of the parties and then executed on. So it handles all of the networking, the MPC protocol choice, the parameters, and then spits out like the result of an MPC computation. And we also have reasonable defaults for this. But if you're like a bit more advanced, then you also have the ability to change your parameters accordingly. But now that you've like ran your MPC computation, you want to be able to use that result in your end application. That end application can be a web app, it can be a blockchain, it can be anything really. But in order to do that, you need SDKs. So right now we have a Python SDK, and then our Rust code is like all crates, so you can use it as an SDK, but it's not like packaged nicely in an SDK quite yet. But it's all open source and available. And then right now we're working on TypeScript and Solidity SDKs, so that if you're building a TypeScript app, you can just integrate the stuff in the previous step into it. And then if you're building like an EVM-enabled app, then you can also get the result of an off-chain MPC computation on-chain. So this is basically a way to get the actual MPC computation into your app. And you don't need to rewrite your entire app. You can just have parts of your app be executed in MPC, and then the rest of your app stays exactly the same. And so it gives you a lot of options for configurable privacy. So this is what the Python SDK kind of looks like. It has changed since I made these slides. So yeah, there's a discrepancy between what's on the slide and what's actually like in our PRs. So how would this look like for a blockchain app? So basically on your right-hand side, those are clients, and these clients can be users, and they want some MPC compute done over their inputs. So before they even start, they need to sort of get information about the application and request certain public inputs from the chain. Once that's done, then locally they're able to do this secret sharing procedure that I described previously. They send the shares to the MPC network, which is like Stoffel in Armor. These Stoffel and Armor nodes interact with the blockchain. They also get computation instructions and public output and some public output. And they receive the public inputs from the clients. Once they've managed to get all of the inputs for their computation, then they're able to do the computation. Once it's completed, they post the results on chain and directly send the final shares to the clients, and then the clients can reconstruct their information locally. So what have we actually unlocked? So the first thing is you can take like any function that's useful to you, and now you can split it across multiple different parties. The next one is for any encrypted input, you get encrypted output as a result of having these three parties that compute the function without knowing the inputs. And during the actual execution of it, you don't need to decrypt your inputs, which is like also pretty powerful, and it's like kind of the point of using MPC. So as a result, you can take any functionality that you're familiar with, and you automatically get these nice properties. So it does open up a wide range of functionality that is done within a confidential compute environment. So this is more of like, how can you actually use this? The previous slide might have seemed kind of abstract. So we'll go quickly over an example of how this is used. So a case study that we wrote a while ago is called Honey Badger Swap. It's basically Uniswap, but executed in an MPC environment. So if you know Uniswap, you know that it does a constant market maker. So basically x times y is equal to k. X and y represent the sizes of pools of different assets, and k is some constant. And it's initialized when whoever creates that pool for this pair decides to set the price for these assets. So in order to swap it, It's by that formula up there. So basically, if you wanted to implement this in MPC, you're basically implementing this b equals y minus k over x plus a function. So roughly the flow is that the client who's trying to do trades in our Honey Badger swap system, first they need to sort of request info from the smart contracts and initialize some constants. In the demo that we wrote a few years ago, basically, the clients had to initialize into a new kind of account. And this was kind of like a private account where the amount was hidden. But then they still had to do some off-chain processes, which they still need to do. And so yeah, that's the first step. The next step is the amounts that they actually want to trade. They would encrypt it, and then also indicate like what direction they want to trade it in, whether they want to trade like sell asset A for asset B or vice versa. Then once all this is sent to the MPC nodes and some metadata is sent over to the smart contract, the MPC nodes wait until enough inputs get added to the smart contract and they receive enough inputs, and then that's when they execute the computation. This was typically done in batches because Uniswap requires shared state. And so once this is done, then the result of the computation is posted on chain, but then the actual amounts that the clients requested get sent to them, and then they're able to withdraw the exact amount on chain, from the chain. And like mentioned previously, they would decrypt locally. So basically, this gives you a form of dark pool for Uniswap, where you leak very little information about what you've traded and how much you've traded. So what's the status of this now? So as I've mentioned earlier, we're still pretty early, but a lot of the components are kind of ready to play with right now. They're not production ready quite yet. We just shipped our doc site today. It's still kind of rough, but you can still sort of try it out, give me some feedback. I'll be here all week. Right now we are working on some utilities to make it easier. Well, I should also mention, you can't run this yet. Soon, there's some PRs waiting. So yeah, we've made MPC practical today. I mean, it was always practical, but we've made it like more developer friendly. You also don't need a PhD to be able to use this stuff. We've put a lot of effort into making it really accessible. And now you don't have to completely shut off privacy and utility in your apps because you have a way to replicate the functionality that you want to implement, but in an MPC environment instead of just a regular clear text environment. So yeah, thank you for listening. That's the end of my talk. If you want to learn more about what we've been up to, you can scan the QR code up there. That's me on Twitter, @CryptoBitch, and that's me on Telegram, just my first name, Mikerah. And yeah, that's it.
ありがとうございました。Thank you very much.